what I covered in class was for acidic and neutral solutions. And normally we'll just tell you if it's acidic. If it's acidic solution, there's H plus present. Normally when we balance out the hydrogens, we add H plus. But what if the solution's basic? If the solution's basic, then the H plus is strong acid. Strong acids are going to react with base and neutralize. And so if the solution's basic, then what happens is all the H plus gets attacked. And so what we have to do is we have to do an additional step at the end of those types. And so basic solution, basic solutions, there are actually just pretty much one additional step in basic solution. So the one extra step is you add OH minus to both sides. The number of OH minuses has to equal the number of H pluses on either side. And then you just simplify it as usual. What's going to happen is the H plus and the OH minus is going to combine to form H2O. And so for each H plus we have, we're going to neutralize that to H2O liquid. Because again, in a basic solution, H plus is not going to be stable. Was that the only part, or do you want me to go through an example of that?
I mean, I haven't tried it with it. Could you do an example? Could you do 39A?
Oh, all right. So 39A. Can you give me the reactants that they give?
MnO2 solid.
MnO2 solid.
Plus ClO3 minus.
ClO3 minus.
Goes to MnO4 minus plus Cl minus.
So what we can do here is you can get we don't have to do this, but you could do this right now. Do you see what's happening here? This is a redox reaction. And what's the oxidation state of manganese over here? +4. This is called manganese 4 oxide. And then what's the oxidation state of manganese over here? +7. So we're going from +4 manganese to +7 manganese. So that's losing electrons. That means it's oxidized. If something is oxidized, it's lost electrons. So we have this to help us remind ourselves what's happening here. Sometimes it gets a little bit confusing, but that's because we have oxidizing agents and reducing agents. But oxidation is loss, oil, and then the rig is reduction is gain. So oxidation is loss of electrons. So MnO2 was oxidized to MnO4 minus. Well, if it was oxidized, who did the oxidizing? And who did the oxidizing is the oxidizing agent. And so in this case, who must have been the oxidizing agent? Must be this, right? Chlorate. Chlorate, what's the oxidation state on chlorine and chlorate?
+6.
+5. +5. And then it's going to -1. Okay, we don't have to do this. We could see this in the half reactions. When we do the balanced half reactions, we can see who's gaining, who's losing. And so we split this up. MnO2 goes to MnO4 minus. The first thing I do is I look, is this one of the reactions on our chart? Was this one of the reactions on the chart? Did I post the chart? Or I haven't posted the chart? I haven't posted the chart yet. Shoot.
Forgot to do that.
Well, it's also in the book. That chart is from chapter 19. So the first thing I do is I look. If this is one of the ones off the chart, then I should save a lot of time. Likewise, I do the same thing for the other half. The other half is chlorate goes to chloride. I look, is this one on the chart? So let's just take a quick look at the chart and see. I'll post that. Okay. What I like to do with charts like this is I don't like to memorize them, but that doesn't mean I completely ignore them. So what I like to do with charts like this is I wouldn't do this every day. Like, you know, tips for studying. One of the tips I gave you for studying is to review your notes every day. If you review your notes every day, then by the time the exam comes, you have everything memorized. If you did the same thing to this chart, I don't review this every day, but I'd review this. I would have a schedule. I would just review this every once in a while. The reason I'd review it is just to familiarize myself with oxidizers and reducers. So the strongest oxidizer is fluorine. So fluorine's an oxidizer, but it's reduced in the process. So reduction is gain, rig. And so it's gaining electrons. So fluorine oxidizes something and is reduced in the process. And so we have to get familiar. It takes some time for those to click for some people. But here, fluorine's the strongest, and then what? Oxygen, and then there's this disulfate thing, which is more of a peroxide thing we had talked about. And then hydrogen peroxide and permanganate. Oh, here's permanganate. So there's permanganate here. But the problem is this permanganate goes to Mn2+, whereas this permanganate doesn't go to Mn2+, it's from MnO2. So unfortunately this one won't work because rather than if this were MnO2, then it would be perfect. We could just copy it. And then what's this? Yeah, lead 4 oxide. There, lead 2 and lead 4, and then chlorine, dichromate. This MnO2. This is manganese 4 oxide, and that's going to Mn2+. It doesn't work either. So these two were close, but not quite. And then oxygen. You start to notice some patterns. You know, if you go through these, you start to wonder about certain things. You know, if you never look at this, then you'll never be curious about these things. But do you see this? Ozone plus H plus, hydrogen peroxide plus H plus, permanganate plus lead 4 oxide plus chlorine. There's no H plus. Dichromate H plus. MnO2 H plus. O2 H plus. What's going on with all those H pluses? Do you see a pattern? But what's the pattern?
They're acting as protons.
Yeah, I mean they are protons, so they're pretty good actors.
They're acting as a way for the electrons to
No, the electrons aren't moving with H pluses. If we look at let's go to oxygen here. It's H plus. What's the oxidation state of hydrogen in water? Did the oxidation state change? No, so it's not really participating. It's not participating in the redox part, but it is participating in something else. Yeah, it's a Bronsted or Lewis. It's acid base. And the reason we need the H plus is if there wasn't H plus on water, then what would we be left with? There's no H plus, no H at all. If there's no H at all, what would we oxide? Is oxide very stable in water? No, we know oxide is not stable, and so the H plus is critical in making a stable product. Otherwise, if we don't form water, we're going to form oxide, and oxide alone is not going to be very happy. So all these are oxygen containing. Dichromate has oxygen, that's why there's H plus. Permanganate, we can easily figure out how many. 4 oxygens is going to need how many H pluses? 8. Now, that doesn't work for everything because sometimes we form like hydroxide, sometimes. But look at 2 oxygens needs 7 oxygens needs 14. So you can see it easily unless there's hydroxide that forms here, but it's not going to be here, it's going to be down in the other table below. This one we can't though. Nitrate, it doesn't work for nitrate. Why? Because if we have 3 oxygens, we should have how many H pluses? It should be 6. And the reason is because one of the oxygens ends up staying in nitrogen. And so only 2 of the oxygens are here. Therefore, we only need 4 H pluses. So these are the types of patterns that you see if you do it once in a while. You know, once in a while you'll look through these, and then the other thing you'll recognize are some of the powerful oxidizers, you know, and some of the very weak ones and the moderate ones. So as we continue down, what's this one? Iodate. Well, iodate is somewhat similar to chlorate, and so here we have iodate plus how many H pluses? But this is going to iodine, not iodide. So this one doesn't quite work. It's not the same. You know, it's a little bit different pattern. If this were chlorate going to chlorine, then it would have worked. We could have used that as a model and had done that way. Then we have what? Not bromide. Bromine. Bromine liquid. So the ranking goes fluorine's the most powerful, then chlorine, then bromine, and then what would be below bromine? No, in the same family. The halogens. Fluorine's the most powerful, followed by chlorine, followed by bromine, followed by iodine. So iodine should be somewhere down here, right? We could predict that. If iodine wasn't on the chart, we could have predicted that, right? Just based on patterns that we see when we review such stuff. And then we have nitrate. Now the interesting thing about nitrate is not that powerful unless there's what present? Nitrate needs H plus. And so we need acid. It could be nitric acid. Nitric acid is perfect. If we have nitric acid, then only one of the nitrates out of the 4, if we had 4 nitric acids, only one of the nitrates react. The other 3 would be spectators in this particular reaction. And so here, it doesn't matter what the ratio. The ratio is just going to tell you, you know, we just need the ingredients. So we can just take a nitrate salt and some acid. It doesn't matter where the acid comes from, just any acid. And that's going to make a powerful oxidizer. Nitrate plus acid is a powerful oxidizer. Now, if there's no acid, then it's not going to form water. Water, we need that to form. It's going to be more stable. You know, we'll have some oxide, and it's going to be unstable, so it's not going to be as reactive. And so if we don't have H+, what happens is nitrate drops in ranking way down here. With H+, it's up here. Followed by silver ions. Yeah, it's +1, but it's a surprisingly good oxidizer. That's because silver metal is so stable. Another unusual one is this. What's next after silver ion? Iron 3. That's kind of interesting because iron 3 is actually really a pretty decent oxidizer here. So you think about rust. Rust as being a good oxidizer. Well, the problem with rust is the iron 3 is locked in a lattice. And so it makes it difficult for it to react. But if we had iron 3 aqueous, then yeah, it's going to be pretty reactive. It's a decent oxidizer. And then this oxygen isn't as good, so we use the above oxygen here. So let's skip this one. Iodine, well here's our iodine. Copper 2. Sulfate. Sulfate's an oxidizing acid. You see sulfate and acid. The reason they split it up like this, because when we think about it, the major species here would be bisulfate, but But the way we formed this, or sulfuric acid, in this case this would be sulfuric acid, so why didn't they just say H2SO4? It's because we can take any sulfate salt and any acid and mix them together, and that would give us this combination. And so we don't split up sulfuric acid like this. It's just this way. Tin 4 is a high charge, you know, but not a super powerful oxidizer. Sulfur, this is really weird. Sulfur can go either way. Sulfur can lose. Sulfur is normally thought of as a pretty decent reducing agent. And here it can be an oxidizer as well. You think it's in the same family as oxygen, so you think it'd be a pretty strong oxidizer like oxygen, but it's big. It's a big atom. So this is very similar to the kind of O2. And rather than forming H2O, it forms H2S. And then we have H+, just acid, mineral acid, etc. So we go down the list, you know, once in a while, and then we go up the list here for reducers. Lithium, potassium, calcium, you know, the alkali metals, the alkaline earth metals are all good. Aluminum, zinc. Zinc is very good reducer. Iron, tin, etc. Up to the worst, which would be fluoride, would be the worst. Yeah. Reducers lose electrons, so these are oxidized in the process. Going backwards here, fluoride loses electrons to form fluorine going backwards. And then we have this bottom one. You know, these are in basic solution, so we can't have H+ in basic solution. So for example, this one, you know, we might try to form H+, but it's not, it can have hydroxide in basic solution, so we see hydroxide here rather than H+. Over here, we aren't going to have H+. You know, we have one oxygen or one oxygen. How many hydrogens do we want? You know, this kind of thing. Well, we aren't going to have H+ here. In this case, we're just going to have H2O. That's going to be our source of hydrogen. So anyway, ozone, hypochlorite. Ozone can be in basic and acidic solution. Hypochlorite here is usually in basic solution. Oxygen can be in both. Water is in basic solution here. All right, did we have chlorate? We didn't have either of these, so what we have to do is we have to do both of these, unfortunately. So the manganese is already balanced. So we don't have to do anything. And then we have 2 oxygens, 4 oxygens. And then we're going to add 2 waters over here. And that's going to give us a total of 4 hydrogens over here and 0. And so we'll just add 4H+ over here. And then the charge, -1 plus 4 is going to give us +3. This is going to be 0, so +3 electrons. So we're going to have MnO2 solid plus 2 H2O liquid is going to yield permanganate plus 4H plus 3 electrons. Okay, this is fine in acidic solution. This would not be fine in basic solution. So there are different ways that people handle this. Some people go ahead and neutralize all the acid here, but I don't. I wait until the very end, because if I do it here, then I'd have to do 2 steps. I'd rather just do 1 step in this. And then we can balance this one. The chlorines are balanced. And then we have 3 oxygens and then no oxygens, so we'll need 3 waters. And then we have 6 hydrogens and 0 hydrogens here, so we'll need 6H+. And then that's -1 plus 6 is +5, and then -1 plus 0 is -1. So how can I get these to equal here? 5 electrons won't do it. I need 6 electrons to get the -1 and -1 on both sides. So this is going to give chlorate plus 6H plus 6 electrons goes to chloride plus 3 H2O. So far everything's the same. Okay, so we'll add it up. I have 3 electrons here, 6 electrons here, so this one I'm just going to multiply by 2. So this is going to give me 2 MnO2 solids plus 4 H2O liquids plus chlorate, ClO3 minus, plus 6H plus 6 electrons yields 2 permanganate plus 8H plus 6 electrons plus a chloride plus 3 waters. And then simplify it. 6 electrons here, 6 electrons here. The 6 H pluses will cancel 6 out of the 8, so that leaves us with 2 H pluses here. And then I have 3 waters here. I'll cancel 3 out of the 4, and that's just going to leave me with 1 water. And so I have 2 H pluses. It doesn't matter what side the H plus is on. It has to be neutralized. So if I have 2 H pluses here, that means I have to add 2 hydroxides to both sides. I have to add it to both sides. Otherwise, I just screwed up the balance. And so adding it to both sides, I'm going to get 2 MnO2 solids plus an H2O liquid plus chlorate plus 2 hydroxides. This is going to yield 2 permanganates plus, okay, now I have 2 H pluses plus 2 hydroxides is going to give me 2 waters plus chloride. I only do this step if it's basic solution. If it's acidic solution, I wouldn't have done this. I would just simplified it as we did here and rewrite it. But this is the extra step right here. Okay, now we'll simplify again. There's 1 water here. I can cancel 1 out of the 2 here. And so this should be it. And so this is going to give me 2 MnO2 solid plus chlorate plus 2 hydroxide plus 2 MnO4 minus plus H2O liquid plus chloride. Now, for skeleton redox, there was driving force present. Driving force, all skeleton redox. There's a driving force present. Otherwise, we wouldn't have gotten any product. And so we know that we must be going from stronger to weaker here. The easiest place to analyze this is the analysis for experiment 18. Experiment 18 is looking at this. That means when we look at this, is this losing electrons or gaining electrons? Going left to right. Electrons are over here. That's a losing electrons. So this is being oxidized. If this is being oxidized, this must be the reducing agent. Reducing agents lose electrons. And so this is our reducing agent. And that means this must be our oxidizing agent going backwards. So this is the conjugate pair here. This is gaining electrons, so this is the oxidizing agent going in the forward direction. Going in the reverse direction, this would be our reducing agent. So this is our conjugate pair. So we know that this has got to be a stronger reducing agent, and this has got to be a weaker reducing agent. This has got to be a stronger oxidizing agent. This has got to be a weaker oxidizing agent. So if we were to rank these in terms of oxidizers and reducers, this is what we're going to have. So MnO2 is going to be our reducing agent. Chlorate is going to be our oxidizing agent. Here. Permanganate will be our oxidizing agent going backwards. And chloride will be our reducing agent going backwards. And so this is going stronger, stronger to weaker, weaker. And so in experiment 18, we will generate our chart like this. These two things are not on our chart, but we can place them relative to one another. Oops, I didn't want to erase this, but I did. So what that means is that chlorate is a more powerful oxidizer than permanganate. So here's permanganate. That means chlorate is up here. That kind of makes sense. Iodate's here, and chlorine's going to be more powerful. Well, the conjugates are going to have the reverse trend. And so that means the conjugates would be chloride and MnO2. And so MnO2 is going to be a stronger reducer than chloride, whereas chlorate is going to be a stronger oxidizer than permanganate. So this is what we do with the, if we have the, you know, if there's a driving force and we want to analyze it, the ranking. And so this was what the pre-lab was all about on experiment 18. What I'm going to do though is I'm going to do it differently. Since we already have the chart, we're just going to use the chart to predict the reactions. Does this answer the question? Was there any other question? So we're not going to do this ranking system. We're just going to predict the reactions first and then do them. All right, you can work with a partner for this, but what I want you to do is I want you to work together. I.e., I don't want you to split the workload, like you do half, I do the other half kind of thing. You should just do them together. Otherwise, I'll have to have you work individually. So I want you to see all the observations. I'm going to leave the redox chart up. And then we'll just predict it based on the redox chart. Okay, so it says work in pairs. 1 milliliter portions. Do you know how much 1 milliliter is? You're using these little plastic pipettes here. So 1 milliliter is 1 squirt of the pipette. You don't have to measure it out with a grad cylinder. We don't have to be very precise in this particular experiment. We can just do it very quickly. And it doesn't really matter necessarily how or what order you do it in. And so let's take a look at the first one. Now, they say to sand the metals, but I say we don't have to sand the metal. I don't want you to sand the lead metal. So don't sand the lead metal. We don't want you to generate lead dust that you inhale and touch with your skin. End up getting lead poisoning. So we're going to test some metals. Actually, the first metals we're going to test are copper. So let's do that. You can also recognize what type of reaction this is. So we're going to take copper metal and react it with lead 2 sulfate. Is it right? Lead 2 sulfate. 0.1 mole. There's something very wrong with that. What's wrong with lead 2 sulfate, 0.1 molar? Sulfates are all soluble except for
Lead.
silver's asterisk. Silver, lead, mercury, calcium, strontium, barium. Lead 2 sulfate, this should not be aqueous. So maybe we're reacting with solid, but solid to solid reactions are very slow. So there's something wrong with this right off. So let's see what lead salt we're working with. What do you think the lead is going to be? So that's a typo. Is that what's shown in your book? Lead 2 sulfate solid? I mean aqueous?
It doesn't say aqueous, but it is listed under solutions, so.
Oh, I don't know. I'm looking at page 18.5. It says lead 2 sulfate? All right, then we don't want that. This is wrong. This is going to be lead 2 nitrate. The bottle is located in hood number 3 over there. Now with lead, be careful. You don't want to get anything on your fingers. Also, usually after you handle things like that, you want to wash your hands, so you don't contaminate yourself or anything else. Anyway, these are all going to behave, I think, for single replacement because we're using mineral acid and we aren't using anything really powerful as a reducer or anything else. So these should all be single replacement style. So this is A plus BX. What does it form? Copper 1 or copper 2?
Copper 2.
Copper 2,
Nitrate.
nitrate, and
Lead.
lead. And then with this, we use the activity series. So our chart is the upside down activity series. Let's take a look. Lithium is the most active. And then we're comparing copper and lead. Which one's more active? Well, here's lead here. And here's copper here. So which one's more active, lead or copper?
Lead.
Lead. So we're going from less active to more active. And therefore, we expect NR. The driving force should be in the reverse direction here. So this first one, we're looking for no reaction. So you would just want to verify that. Okay, next, we're taking our copper metal and zinc nitrate solution. There's only one zinc, and it's zinc 2+, zinc ion. And so let's go ahead with this. Now, wait a minute. Nitrate. Didn't I say nitrate is a more powerful oxidizer than a lot of stuff? So when I compare this, this is lead 2 and nitrate. So something doesn't quite click here. Because I have lead 2 and I have nitrate. And when I look at it, here's lead 2, where's nitrate? Which one's a stronger, more powerful oxidizer? Nitrate is way more powerful. And the single replacement is saying who's taking the electron? Lead. And who's the spectator? Nitrate. Does that make sense to you? No, it doesn't make sense. The only reason this makes sense is because nitrate's missing something. What is it missing? H+. Since nitrate's missing H+, its ranking drops way down. If there was acid present, then for sure nitrate would be reacting. And so this has got to be in a neutral or maybe a basic solution. If this were in an acidic solution, then nitrate's going to be reacting and forming NOx, oxides of nitrogen. You'll start to see NO. Well, you can't see NO because it's colorless, but the NO gets oxidized to NO2, which is orange. And so the reason why single replacement works here is special because we're not doing this in acidic solution. If we were doing this in acidic solution, forget it. It's not going to work. We can't use single replacement. Does that make sense? But we're lucky because if we can use a single replacement, I'd have to use a chart. The chart's not hard. It just takes more time, and I don't have the time right now to to do the chart method, so I want to use the single replacement. Is that clear though for everybody? Okay. So the same thing here. Nitrate's more powerful, but we're missing H+. It's like the analogy I always use is like this. Let's say you're trying to make cookies and you need 4 cups of flour. The 4 cups would be the 4 H pluses and 1 cup of sugar. But you have no flour. Are you going to make any cookies? No. And so the same thing. We're not going to make any water. That's okay. That means that's going to delegate zinc as the oxidizer in this case, although this is going to be tight, but there's no reaction regardless either way. So this is going to make copper 2 nitrate and zinc metal. And then we compare the activity series. You probably already know which one's more reactive, zinc metal or copper. Zinc. Zinc metal's here, copper's up here. Zinc is much more active. It's much easier to oxidize. And so what we say here is no reaction. So more active, less active. What this means is this is a weaker reducing agent, and this is a stronger reducing agent. That's what activity series is. The activity series is the strength as a reducing agent. So 2 no reactions. Okay, now we're going to silver nitrate. So copper solid plus silver nitrate. Silver also is fixed charge, only 1 charge on that. And so this is going to form copper 2 nitrate and silver metal. And then let's compare copper with silver. Okay, here's copper here, here's silver here. Which one's more active? Copper. And so copper is a stronger reducing agent, and this is going to a weaker reducing agent. We have 2 activities. We have activity as a reducer and activity as an oxidizer. And so here we have reaction. And so we'll need 2 silver nitrates, and this is going to form 2 silvers. Now this one, if you look at the report sheet, it does it in net ionic form. And so what we'll do is this is the ionic equation. I mean, this is the CE, the conventional equation, and then the complete equation. Then we have the ionic equation. Copper is not a strong acid. It's not a soluble salt, therefore leave it alone. However, silver nitrate, all nitrate salts are soluble. So this is going to give us 2 silvers, 2 nitrates. And copper 2 nitrate soluble as well. All nitrate salts are soluble. And silver just stays alone. I don't know how many people ionize this. I don't understand why. If we have copper metal, then they ionize it to copper 2, but we don't have copper 2, we have copper metal. Copper 2 is the blue solution. And the same thing with silver. For some reason, going from the CE to the IE, they put a charge on there. It doesn't change identities. Okay, in this case, the nitrate, even though it's a powerful oxidizer, it needs the H+, and therefore it's just a spectator in this particular reaction. And we end up with this. So here, we expect reaction there. And then copper metal with HCl. Copper metal with HCl. HCl is a mineral acid. And so we're okay here. Chloride is going to be a spectator in this case. It's not an oxidizer. So this is going to form copper 2 chloride plus H2 gas. We'll need 2 HCl's to balance this. We compare copper with hydrogen. Hydrogen's down here. Copper's up here, so hydrogen's more active. So in other words, we're going from a weaker oxidizing agent to a stronger oxidizing agent. Now they ask you to sand your pennies, but there could be a side reaction that occurs here. I'm going to ask you not to sand any of the metals. You don't have to sand any of the metals. It slows the reaction down, but they should react okay. And so skip the sanding part. The side reaction is if there's copper 2 oxide or copper 1 oxide. Copper 2 oxide is black, copper 1 oxide is brown. So if you have a brown or a black coating on the penny, then the acid can successfully react with the coating and remove the oxide coating on there. And so with HCl, this is a double replacement. What forms here?
Was it copper chloride 2?
Yeah, copper 2 chloride and
Water.
water. So we have 2 HCl's. The driving force for this is stronger acid to weaker acid. And so what happens is it'll eat up the coating, and then once it hits the copper metal, it'll stop because it won't react with the copper metal. So it'll make your pennies shiny if you add acid to them. And the same thing here with the copper 1 oxide, the brown oxide. This is going to form 2 copper 2 chlorides plus. How many waters? 1 water. Is that right? No, that's not right. Yeah, this is not unbalanced. You can balance it. I don't want to spend too much time because I gotta get through these. Okay, let's take a look at the next series. We're going to test lead metal. You know what? Let's skip all the lead metals. Unless, do you want to do the lead metals? No? Not particularly. Actually, let's do this. We already know what's going to happen with the copper and the lead 2 sulfate. Let's skip the lead solution. I don't want to poison there, especially if you're in a rush to finish it. So we're going to skip lead metal and lead 2 nitrate solution. Of course, we can do it safely, but you know, you do things safely, you should do them slow and methodically. And so we're going to skip all those, and we'll go to zinc. Zinc is not a problem. Zinc plus copper 2 sulfate. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this is going to be soluble. What forms here?
Zinc sulfate plus copper.
Yeah, zinc sulfate plus
Copper 2.
no, copper 2?
Copper solid.
Copper solid. Copper. A plus Bx yields Ax plus B. B is going to be elemental. Now sulfate is an oxidizer too. Do you see sulfate here? This is an oxidizer as well. But it's weaker than copper 2. Moreover, sulfate needs acid. We don't have acid. So copper 2 is going to be it regardless. Even if we had acid, copper 2 would be it because it's stronger. And so we expect reaction here. Well, do we expect reaction? So we're going from zinc to copper. Do we expect reaction? Or no reaction? No reaction. Because copper is more stable. If it's more stable, it's weaker. It's a weaker reducing agent. Copper is more stable than zinc. And so this is a stronger reducing agent. It's easier to oxidize. This is a weaker reducing agent, so no reaction. So you're going to look for no reaction on that first one. We're going to skip the lead, as I mentioned, and then we're going to go to silver. Now silver, do you know silver is also a heavy metal, like lead? But it's a little different than, it's very reactive. So if you do spill some on your skin, it's immediately going to react to make, and people wear silver jewelry too, right, without dying. But do you know what silver looks like on your skin? It looks like this. Do you see this? Except the thing is, I can wash this off. But with silver stains, are you going to be able to wash it off? No. So I remember one Chem 4 lab, probably you might have heard this before, but I had a student who was, you know, they were at the sink, they were washing their hands for like 20 minutes. And then finally, they came up to me and said, you know, I have an important job interview right after class, but I noticed their hands had blotches of silver nitrate stains, black stains on them. And unfortunately, you can't wash them off. Eventually it will come off, but can. And so watch out, don't spill silver nitrate on your skin, because silver nitrate is a good, well, silver ions, nitrate's a great oxidizer. You know what nitric acid? This is the combination, black and yellow stains on your skin. Black from silver nitrate, yellow from nitric acid. Because both of them are good oxidizers. But we don't have any acid. And so silver ions are really a pretty good oxidizer. Silver ions will oxidize your skin, your eyes, whatever, and deposit tiny crystals of silver. Do you know what tiny crystals of silver look like? What color they are? They aren't silver. Tiny crystals of silver are actually what color? Black. And so what you have are you have little tiny crystals of silver that just precipitate in your skin. They're very difficult to get out of there. So it's not like you can wash them off. You just have to wait for it to shut off. So anyway, good oxidizer. And so you don't want to get this in your eyes, and you want to avoid contact in your skin. So just make sure there's no spills around there. You'll know because you'll get splotches in your hands, which I mean I've gotten them myself. Lots of nitric acid splotches, lots of silver nitrate splotches. Okay, so what was the reaction we're looking at?
We were looking at zinc and copper sulfate. You said no reaction.
No reaction. Okay, and then now we're at zinc and silver nitrate. Did I just do that? Or we haven't done that yet? Did I already do it?
We talked about it, we tried to do it.
So we're going to form zinc nitrate and silver metal. There's definitely going to be a reaction here. This is a stronger reducer and silver is a weaker reducer. So we're going to get a reaction. And this is a CE, so we'll do the IE. This is going to give us 2 silvers, 2 nitrates. This is going to go to Zn2 plus 2 nitrates plus 2 silver metals. And the spectator will be nitrate, and so we'll have Zn solid being attacked by 2 silver ions to form Zn2 plus 2 silvers. So we predict a precipitate of silver metal. That's what we should see, a precipitate of silver metal, and the zinc metal should start to be eaten away, reacted. Okay, let's go to zinc and HCl. This is going to form ZnCl2 plus H2 gas. I'll just speed things up a little bit here. When we come here to zinc and hydrogen, zinc turns out to be a weaker, or actually stronger reducing agent. Hydrogen turns out to be a weaker reducing agent. It's less active. So we're going from more active to less active. So we expect a driving force for this particular reaction. So we're going to write out the ionic equation. Is HCl a mineral acid or oxidizing acid? Mineral acid or oxidizing acid? Mineral acid. Otherwise, we wouldn't do single replacement. And so we should form bubbles of hydrogen gas. So you should notice some effervescence with the zinc. You might have done this in Chem 4, ignited the hydrogen gas.
Just right now.
Uh-huh.
Did you run back to the zinc and copper sulfate?
Mm-hmm.
Explain why it's not reaction.
Isn't it reactive to
Oh, right.
So isn't that a reaction?
Yeah, there is a reaction. Yeah, that's wrong. What I said was wrong. There is a reaction there. Zinc is easier to oxidize than copper. So there is a reaction. So we should do the ionic equation. So I'll just write the ionic equation here. And then the net ionic equation. Zinc is going to be oxidized by copper 2 ions to form zinc ions plus copper metal. And so, yeah, there is a reaction. All right, okay, now we're going to go to the halogens. Sorry, let me erase this here. All right, chlorine, bromine, and iodine. Chlorine, bromine, and iodine. You know, chlorine is kind of yellow, bromine is kind of an orange, and iodine is purple. These are the colors for these. So in part A, we're going to make chloroform control samples. These are all non-polar. And then we're going to use this stuff, CHCl3. This is trichloromethane or chloroform. Chloroform is, for the most part, non-polar. You know, very slightly polar. But it's like an oil, but it's very dense. The density of chloroform is greater than water. It's a liquid. It's a CCl, clear colorless liquid. The density of CHCl3 is greater than the density of water. They don't mix. And so this is like oil and water, but most oil floats on the surface of water. This oil sinks to the bottom of the water. So this is an oil that sinks to the bottom of the test tube. So we're going to do what's called a solvent extraction. If we have chlorine water, do they like each other? Chlorine, aqueous. Chlorine is non-polar, water is polar. Do they like each other? Not that much. But can you form chlorine water? Yes, you can. You know, some chlorine will dissolve in water, just like O2. Some O2 dissolves in water, otherwise a fish can't survive. You know, O2 is non-polar too. So some chlorine gets in the water, but you know what chlorine would much rather be dissolved in?
Yes.
Yeah, gas. Gases make nice solutions. But what liquid would chlorine rather be dissolved in? Chloroform. Chlorine likes chloroform much more than water. So what we're going to do is we're going to just put a few drops of chloroform in here. Where does the chloroform sink to?
Bottom.
Sinks to the bottom. So just put a little bit of chloroform in here. A few drops. The more chloroform you put in there, the harder it is to see the colors. And so I would just put like 3 drops. No more than 3 drops maybe. Let's say a few drops. You could add more if it's too little. They ask for too much. There's some people who put like a milliliter of chloroform in there and the colors are awful. They don't get very bright colors. Colors are so weak. This is also something you don't want a lot of chloroform because chloroform, even though it's more dense than water, it's fairly volatile. So what we're going to do is we're going to cap this with a cork and seal it as tightly as we can. Like this. And then we're going to put our thumb on top of this so it doesn't come off. Because you don't want to shake this. You're going to shake it. You don't want to shake it and then spray a whole bunch of chloroform and chlorine water on your hands. It's not good. And the problem is since this is a little bit volatile, it's going to generate a little bit of pressure here. So sometimes what people do is they release the pressure a little bit, in the hood. But here, I don't think we're going to, if it's just a few drops, I don't think we're going to have to worry. This is people who go crazy with chloroform. And then what happens is they're shaking it, and the, and the cork pops off, and then all the liquid goes on their hand and arm. It's happened many times. So we should be all right, though. Okay, and then what we're going to do is we're going to shake this. And you can put a cork, make sure the cork is well sealed, or what I do sometimes is I line the cork with parafilm. I don't think we have any parafilm, though. If you use a natural wood cork, the cork wood, I don't think those, I'd rather use a rubber stopper on this. The wood corks are porous, and sometimes they don't seal very well. If the pore is there, the seal's not so good. So I recommend rubber stopper for this. And then shake it up. What you're doing is just shaking, and then you're going to disperse this as emulsion. Like, emulsion is like having little tiny droplets of oil dispersed in here. There are emulsifiers that stabilize that, like in mayonnaise. In mayonnaise, they can disperse the fat throughout uniformly. But what's going to happen is we don't have an emulsifier. What's going to happen is those little tiny oil droplets are going to come back and coalesce and form this little layer of oil at the bottom. Okay, but what we want to do is we want to shake it up, make an emulsion so that chlorine comes into contact with these oil droplets. When chlorine comes into contact with the oil droplets, then what's going to happen is we're going to transfer the chlorine from the aqueous layer to the chloroform layer. So what we should end up here is yellow, hopefully bright yellow. We're not going to extract 100% of the chlorine, but we want to extract enough that we see bright yellow here. So this is called a solvent extraction. Chlorine's more soluble in chloroform, therefore we're going to extract it into chloroform. What do you think is going to happen with bromine? Same thing, but here, rather than getting bright yellow, we're hoping for bright orange. And then for iodine, we're going to hope for bright purple. Yeah. So this is our control. So you want to see what it looks like, and if you're successful at solvent extraction. Okay, then we're going to do the reactions. If there's no reaction, then if we start with chlorine, we're going to end with chlorine. So we can detect the presence of that. Sometimes it's hard to see in the aqueous phase. And so let's take a look at the reactions that we're doing. The first one that we're going to do is we're going to use chlorine water to try to oxidize KBr. So we have chlorine aqueous with KBr. KBr is going to be aqueous too. Now this might look single replacement, but this is a different one. We could use the second single replacement pattern if you memorize it, X2 plus AY pattern. But basically, this is what's going to happen. Chlorine is a great what? Oxidizer, and bromide is a pretty good reducer. Bromide's a much better reducer than water. The only other reducer would be water. Potassium ions are going to be an oxidizer, but potassium ions are at the bottom of the oxidizer hierarchy. So in this case, what we're going to get is we're going to get chlorine oxidizing bromide. So if chlorine oxidizes bromide, then what we should form is KCl and bromine. Aqueous. And to balance this, we'll have to double these. So in other words, if we look at the net ion equation, this is what's going to happen. So we got chlorine aqueous plus 2 potassiums. The potassiums are going to be spectators in this case, and 2 bromides. This is going to go to 2 potassium ions plus 2 chloride ions plus bromine aqueous. So potassium spectate, so chlorine is going to oxidize 2 bromides to produce chloride, 2 chlorides plus bromine. So in this particular reaction, this is bromine aqueous. Bromine aqueous is hard to see, and it's going to be dilute. So we're going to do an extraction. So we're going to do bromine aqueous and then we're going to extract it with chloroform. I'm going to write chloroform above the arrow here. And then what we're going to form is bromine dissolved in chloroform, which we'll write as Br2CHCl3 in parentheses down here, to show we're extracting it to the liquid. And then we should see, this should go bright orange. We expect a reaction here because chlorine is a stronger oxidizer than bromine. Bromine is a weaker oxidizer. So we expect reaction to occur. Okay, then I'm kind of running out of time, so then we're going to do the others. Do you see those? And so you could predict this based on the ranking of the halogens. We know the ranking. We don't even have to look at the chart. Fluorine, chlorine, bromine, iodine, right? That's the ranking. Are you good with this? All right, then we're going to part C. FeCl3, KBr, and FeCl3 plus Ki. So, etc. for this. And then part C, FeCl3 plus KBr. This one has NR for metathesis. There's no metathesis reaction that occurs here. And so what we have to do is we do the chart method for redox. For the chart method, we have iron 3. Iron 3 is what? Iron 3 is a pretty decent oxidizer. We have chloride, which is a pretty bad reducer. Then we have potassium, which is a really bad oxidizer. And then we have bromide, which is a pretty good reducer. And then we have water, which isn't so great oxidizer or reducer. So this is an OA, iron 3. Chloride is an RA. Potassium is an OA. Bromide is an RA. Water is an OA and an RA. So the strongest OA is going to be iron 3. The strongest RA is going to be bromide. So if a reaction is going to occur here, we're going to have iron 3 plus gains an electron. So we can just look here. Iron 3 plus gains an electron to form iron 2. Just copy it off the chart. And bromide, we're going to have 2 bromides go to bromine plus 2 electrons. And then we add it. So we need to multiply the first reaction by 2. And so we're going to get 2 Fe3 plus 2 bromide is going to produce 2 Fe2 plus bromine. And then we'll do the solvent extraction here to see if we detect the presence of bromine. But we can see if there's going to be a reaction here. So what's a stronger oxidizer? Fe3 plus, this is our oxidizer. And in the reverse direction, this would be our oxidizer here. This is our reducer. This is our reducer. So iron 3 plus versus bromine. So here's iron 3 plus. Here's bromine. Which one's stronger?
Bromine.
Bromine's stronger. This is weaker. So I expect no reaction here. We expect NR. But you can check it. Okay, now we're going to do the next reaction, which is going to be FeCl3 plus Ki. FeCl3 plus Ki. Okay, so it's the same thing. Fe3 plus, chloride, potassium ions, iodide, water. OA, RA, OA, RA, OA, RA, both. Iodide's going to be the best, Fe3 plus. So what we're going to end up with here is the same kind of thing. It's going to be 2 Fe3 plus 2 iodides is going to yield 2 Fe2 plus iodine. So we compare iodine versus Fe3 plus. Which one's stronger? Fe3 plus is stronger. So we're going from stronger, I skipped a step here, to weaker, just to save time. And therefore, we want to do solvent extraction here. So what we're going to do is we're going to do the iodine aqueous and then extract it using chloroform to make iodine dissolved in chloroform, which should be bright purple. Next one, we're going to get some small amount of solid potassium permanganate and mix it with HCl. This one we got to do in the hood. Whenever we generate a reactive or corrosive or toxic gas, we should do it in the hood. This one is going to generate that. So we're going to take solid potassium permanganate. You know, when you have a solution, it's dilute, you know, because you're mixing it with other stuff. This is 100% potassium permanganate, which is going to be quite reactive because permanganate is a powerful what? Permanganate is a powerful oxidizer. And we're going to have HCl here. So what is it going to oxidize? Okay, so we're going to do the same thing. Potassium, all potassium salts are soluble, so it's going to dissolve to form potassium ions, permanganate ions, H plus chloride, and one more, water. Now here, OA, we have permanganate, but what else do we need in addition to permanganate? Permanganate needs H plus. So permanganate and H plus, this is an oxidizer. H plus alone is an oxidizer. Chloride is a reducer. Water is both an oxidizer and a reducer. Now when we pick, the strongest oxidizer will be permanganate and H plus, versus H plus alone is a lot weaker. What's the strongest reducer? The strongest reducer turns out to be water. But this is chloride versus water. Chloride versus water, who's going to win?
Chloride.
Chloride. So this goes against the chart. We expect water to be a better reducer. Here's chloride. And we expect water to be a better reducer here. But this is the exception you have to memorize. So we just copy the half reactions off of the chart. Permanganate needs how many hydrogens? You know, 8. So it's going to be permanganate plus 8H plus. And then we'll copy the rest off the chart. So it's off the top here. Plus 5 electrons. Actually, we could figure out how many electrons because permanganate goes from plus 7, in this case, to plus 2. So it's got to be 5 electrons. Plus 7 to plus 2. Plus 4 waters. The other half reaction, we'll just copy the chart. It's going to be 2 chloride goes to chlorine plus 2 electrons. Okay, I'm going to rank these here. This is the oxidizer, this is the conjugate reducer. This is the reducer, this is the conjugate oxidizer. So when we combine these, we're comparing permanganate and acid versus chlorine. So permanganate and acid versus chlorine, which one's stronger? Permanganate and acid stronger. There's going to be a reaction here. So we have to add them up. So what I'm going to do is I'm going to multiply this one by 2 and this one by 5. And so the reaction should be 2 permanganates plus 16 H plus 10 electrons plus 10 chlorides is going to produce 2 Mn2 plus 8 H or 8 H2O, sorry, not H plus 5 chlorine plus 10 electrons. So the 10 electrons cancel. What else cancels? Actually, that's it. And so we're going to end up with 2 permanganates plus 16H plus 10 chlorides produces 2Mn2 plus 8H2O liquid plus 5 chlorine. Now chlorine is not very soluble, so it's going to come off as a gas. So you should see a yellow gas, yellow-green gas, depending on how concentrated it is. And you don't want to breathe this gas here, so you do it in the hood. And there's going to be a driving force because we're going from stronger OA to weaker OA. And the same thing with the RA, stronger RA to weaker RA. And we have driving force for this. Okay, let me try to wrap things up here quickly. Copper and bromine. Copper metal plus bromine. Okay, here we could do the chart method once again. Copper, solid, bromine, water. Copper metal is an RA, bromine is an OA, water is both an OA and an RA. The strongest reducer will be copper, the strongest oxidizer will be bromine according to the chart. Copper solid is going to go to copper 2 ions plus 2 electrons. And then bromine plus 2 electrons goes to 2 bromides. I just copied these off the chart. And so what we're going to have here is copper plus bromine yields copper 2 ion plus 2 bromides. Now we're going to analyze the products. Okay, here this is our RA. This is our RA. So we're going from stronger RA to weaker RA and stronger OA to weaker OA. Since bromine is stronger than copper. Here's bromine, here's copper. Actually, no, bromine is RA. I'm looking at RA. We'll go with the OA. Bromine is stronger than copper 2. Here. So what we're going to do is, this is the product. And so in this we have the copper 2 and the bromine. What we're going to do is divide this into 2 test tubes here. One test tube we're going to test for the presence of bromide. The other test tube we're going to test for the presence of copper 2. So this test tube we're going to add plus 6 molar ammonia. What should happen here is you're going to get a light blue PPT. Because ammonia, what does ammonia do to water? Ammonia hydrolyzes water to form a little bit of,
H4 plus hydroxide.
and the hydroxide with copper 2 will make a precipitate of copper 2 hydroxide. And so the reaction here is copper 2 plus 2 ammonias plus 2 H2O liquid produces copper 2 hydroxide plus 2 ammoniums. But if we continue adding more ammonia, if we get into excess ammonia, what happens is a Lewis acid-base reaction occurs. And that is, this precipitate's going to actually disappear. And so this precipitate's fleeting. You see it 1 minute and the next minute it's gone. Because what happens here is the copper 2 hydroxide is attacked by 4 ammonias. And it produces this weird looking thing, which is going to be Cu with 4 ammonias attached with a 2+ charge. This is aqueous. This is a dark blue solution. Dark blue solution. And so the precipitate disappears and is replaced by a dark blue solution, which we call this tetraamine copper 2 ion, which is in Chem 1b, but this is an example of a Lewis acid-base reaction. Plus 2 hydroxides, plus 2 hydroxides. So the ammonias knock off the hydroxides, and 4 of them attach to the copper 2. This is a Lewis acid base. I need to talk more. I'll talk a little bit more about Lewis acid base later. This is a positive test for copper. If you see this, you might not see this blue precipitate, but if you see this dark blue solution, that means we had copper present. Now the test for bromide is we're going to take this test tube and then we're going to add silver nitrate to this. When we add silver nitrate, what we're going to form is, if there's bromide present, then we're going to form silver bromide, solid. And so you can see what color silver bromide is. Is it white? Is it off-white? What does the precipitate look like? Okay, the final reaction we're going to do is this one. It's going to be silver nitrate and iron 2 sulfate. FeSO4 plus silver nitrate. This is a double replacement. This is going to form silver sulfate plus iron nitrate, iron 2 nitrate. FeSO4 is green. This is a green solution. We need 2 silvers for this. And so we get a PPT. This is a white PPT. However, there's another reaction. This is metathesis. There's a driving force for another reaction, which is redox. For redox, we use the chart method. Iron 2 plus, sulfate, silver ions, nitrate. Iron 2 is both an oxidizing agent and a reducing agent. Iron 2 occurs on both sides. You'll note this if you read the chart once in a while. If you read the chart once in a while, you'll see, oh, there's iron 2 on the left, and here's iron 2 on the right. So it's both. Sulfate is missing something. What's sulfate missing? Missing H+, so we'll ignore it. Silver ions is an oxidizer. Nitrate's missing something. What is it missing? Missing H+. And then we have water, which isn't missing anything, but it isn't very reactive. And so if there's going to be a redox, then it's going to be between silver ions and then iron 2, which will act as a reducing agent in this case. We can get that from the chart. And so here we're going to have iron 2 plus going to iron 3 plus an electron. And then we're going to have silver ions plus an electron going to silver metal. And then what we'll have is iron 2 plus silver ions yields iron 3 plus and silver metal. Initially, the silver metal precipitate will look black, and then eventually, as the crystals grow bigger and bigger, they'll look silver. They'll have that silver color. So this is more complex observation, set of observations, because you'll have 2 different types of reactions occurring. All right, I'm going to stop talking here. Are there any questions? All right, so yeah, all the reagents are in the hoods over there, and then you'll just need test tubes. I have some Sharpies you can use to label your test tubes. And then just try to go through the reactions quickly. If you don't see it and you're expecting an observation, let it sit for a while. So if nothing's happening, but you expect an observation, come back to it later. Move on, so you don't waste any time.